I'm very privileged, and thank you very much for the organizers. Just to give you a little bit of an update of the Square Kilometre Array. Who here knows about the SKA? Oh, gee. Well, well, great, because we started a bit late, so I'll shave maybe half. But at least can give you where things are, because probably the last time you heard about the SKA was like 10 years ago, and you thought that it was already built, or you didn't know what's happening. Maybe you thought that it was going to be in South Africa. Anyway, I will give you an update. So my name is Juan Carlos Guzman, JC, how everyone knows me. I'm the SKA-Low Head of Computing and Software. And I'm really privileged to be in Gunagal country. So I would like to also acknowledge the Wajari Jamaji as the traditional owners and native title holders of the Ingarimana Ilgari Bundara, the CSRO Merchants Radio Astronomy Observatory. Ingarimana Ilgari Bundara means sharing the skies and stars, and it was named from Wajari languages. And it's our privilege and honor to be in their land. We also acknowledge that the Australian indigenous people are the first scientists and have a long-standing knowledge of the universe. And I've seen some of the stories they have told about the emu in the sky. So hopefully this will work.
What did the universe look like when the first galaxies formed?
What are gravitational waves? How does magnetism work throughout the universe?
Come si formano I pianeti?
How many gravitational waves are passing through me right now?
What is dark matter?
What is the impact of magnetic fields on the formation of galaxies?
宇宙の歴史はどうだったか?
¿Estaba Einstein en lo correcto?
And for me, the most important is there life out there?
We ask ourselves, what is the most useful thing that a radio telescope can contribute to the answer to these big questions? We are building a time machine. We're looking at what our surroundings were like almost at their inception. The question is, how are we actually going to make this happen?
And the story begins like that, with questions. Most of the astronomers are experimental scientists. Not all of them, there's theoretical ones. But like any other experimental scientist, the difference with that, the other experimental scientists, like in lab, is our experiment is already running, and that is the universe. So we cannot reproduce the initial conditions; it's just there. So we need to instead to watch it very closely and try to understand those initial conditions where the laws have shaped its evolution, especially the laws of physics. So until very recently, and it wasn't until the gravitational waves, but before that, the only messenger of this information was light, or the electromagnetic radiation. As you can see here in the picture is the electromagnetic spectrum. The pioneers of astronomy, including indigenous astronomers 50,000 years ago, only used that portion, the visible, with all these beautiful colors. But perhaps the most famous pioneer of all of them was Galileo Galilei, who spotted the 4th largest Jupiter moon with his optical refractor 400 years ago. Although that might not be very, very fundamental, and it was very rudimentary, but his discovery just revolutionized science at the time. So if you see the spectrum, hopefully you can see them. So you go from the gamma rays, which are very high energetic radiation, to X-ray, to the visible, all the way to the radio. And all of that nowadays paints the picture of the universe. And in order to understand evolution, we need to understand and try to just make sense of all the radiation from the entire electromagnetic spectrum. We've been building telescopes for decades, for actually hundreds of years, to be honest, since optical ones. But we are now entering into a different era. Over the last decade and going forward the decades, we are now moving into the extremely large telescope. Here is in this slide, we can show from all the way to gamma ray, and on your right-hand side, that's the Cherenkov telescope array, which is currently being built in southern Chile and the Canary Island, which is going to be detecting gamma ray burst, which is a very energetic phenomenon. On the X-ray, most of them are space telescopes. These are, particularly the one at the top, it's called XRISM, which is a collaboration between NASA, ESA, and Japan, who is just going to replace the existing ESA and the Chandra telescope. Then we go to the ultraviolet. And if you don't know, I actually didn't know until last year, there actually we got a telescope based on the moon. It's the Chinese LUT, Lunar-Based Ultraviolet Telescope. Astronomers are really clever in terms of the acronyms, I know. We got in the visible now. We are currently under construction the extremely large telescope. There are telescopes with a diameter of a 40 meter. So I'm not sure whether it'll be the size of this or will be larger than this. So it's a mammoth type of a telescope. There's one being built in Chile, and it's going to also just be revolutionizing science. Then we got the James Webb Telescope, which is kind of on the lower end, the higher end of the infrared. Which was supposed to be replacing the Hubble, but the Hubble is still going. That's also start getting really good science out of that. And then as we move towards the radio wave, we got the microwave, and then we got the radio telescopes. This is where we're building the SKA. And we have already built telescopes since the 40s on the radio side. And now the SKA will be the next time of the frontier. But why radio? Why radio so special? Because the universe is full of dust. And it's a clumps of icy, sooty debris floating in space. And this dust blocks the optical light. This is the Milky Way, as you see in the optical light. But there's a lot of stuff there that just you can't see. So if we use the radio light, the scope of our experiments is only limited by the dimming emission of the objects get further from us. Now, if we can build a sensitive telescope big enough, and measure down to low enough frequencies, we can detect the hydrogen. And hydrogen is a really important element from the very early universe. And this is a picture of how the universe will look in radio. You can see a lot of emission. It's much more active. So if you can detect the hydrogen and measure the frequency shift, then you can map the universe, not in 2 dimensions, but in 3D. And this is a core concept of the SKA. So, back in the early 90s, this is how long we've been actually talking about the SKA. Scientists came up with the concept so-called hydrogen array to detect this hydrogen. And a telescope will be so sensitive enough to detect the signals from the dark ages 13 billion years ago. And to do this, we estimated that we needed a square kilometer array of collecting area. And at the time, this is the rendition of what we will look like. Thousands of antennas, smaller dishes, and then an array there in the middle. To do this, we've been spending decades on designing. And finally, it's here. So what are we building? We're actually building it right now. We're building one observatory. 2 telescopes, one in South Africa and the other one in Australia. And the 3 sites because the headquarters are in the UK. So who are we? We are the SKA Observatory. We are an intergovernmental organization governed by a treaty. SKAO was born on the 4th of February 2021. So then that means in 2 weeks we'll have our birthday. So only second to the IGO in astronomy. European Southern Observatory is the other one. We got 13 countries, full membership, and then others preparing to join. We got 8 African partners countries, which is involved in the coordinating action to support and project the future expansion of the SKA. So our mission is to build and operate cutting-edge radio telescopes to transform our understanding of the universe and deliver benefits to society through global collaboration and innovation. And the last bit of that sentence is through global collaboration and innovation is really true. We have created a large community and we're engaging with community scientists and engineering to build this fantastic instrument. So These are the countries that we are part of it, the Square Kilometre Array Observatory. So we span 13 time zones. So you can see one of the challenges to develop and build this fantastic instrument. So our meetings are, you can tell, spread across. And this is the picture, the map of the Square Kilometre Array membership as of November 2024. Our headquarters are based in the UK, in Manchester, in the Jodrell Bank. This is where you see the Lovell telescope. Very iconic, beautiful area. And the telescopes. The SKA-Mid in South Africa, which is located in the Meerkat National Park in the Karoo region, approximately. It's about 700 kilometers northeast of Cape Town. Regularly, the stuff there goes via plane, which goes daily. You can drive. It takes long, but it's doable. It consists of 197 fully steerable dishes, 15-meter diameter, and will be including the existing Meerkat telescope. The frequency range is between 350 megahertz and 15 gigahertz, so it's the upper band of the radio. It's the maximum distance between the dishes is 150 kilometers, so it's quite a large area. But here in Australia, more specifically in Western Australia, we have the SKA-Low. It's located in the, as I said before, in the Nyarimana Ilgari Bundara, the CSIRO Manchester Radio Astronomy Observatory, approximately 800 kilometers northeast of Perth in the Western Australian outback. Has everyone been in there, in the Western Australian outback? Who has been there? Well, quite a few. So you probably have experienced what is the red dust and the vastness of the area and how flat it is. It's an absolutely beautiful place in this country. And so the SKA-Low will be 131,000 log periodic antenna. They are about this high. They look like a Christmas trees. And every year at Christmas, we decorate the ones that we have in the office. So it's a good time to come and visit us because it's very colorful. Otherwise, they look pretty much metal. They're spread across 512 stations, and we group them in a group of 256 antennas per station, per cluster. So the frequency range is in the lower band. It's a 50 megahertz to 350 megahertz. And the maximum distance between the antenna will be 74 kilometers. And here's a picture of the on your right, or where is located in reference to Perth, where the Science Operations Center and my office is. So the SKA will revolutionize science, but it is an order of magnitudes more powerful than any instrument in the world. It will have up to four times more resolution than the existing instrument, like the VLA in the US. It will have 2 orders of magnitude more faster survey speed, so we can actually do and survey the southern sky much quicker than any other instrument, and will have up to 8 times more sensitivity than any other telescope in the world. So it's just truly remarkable, extra leap in terms of capability. In numbers, the SKA will cost about 1.3 billion euros to construct and 700 million euros to operate over a 10-year period. So it's 8 years of construction. Construction started in 2021, so we're halfway through. We're expecting to conclude the construction in about 3 years from now. And what is exciting is, for those of you who have known the SKA, we've been talking about this instrument for decades. And finally come just to terms with it and actually see it on the ground has been just really, really exciting. And for myself, actually, I remember the first time I went there to see the actual antennas and power them up. A few tears came out of me. I've been involved in this project for 15 years, and just finally seeing that fruition, it's been a real honor and privilege. It will generate 700 petabytes per year once fully built. It will be operating for 50 years. Certainly won't be there by the time we have to decommission it, so it won't be my problem. not sure, it's probably going to be more than 50. So why do we do this? So being a large-scale instrument, studying the dark ages, which is the original concept in the 90s, is not the only thing this instrument will be capable of doing. So in 2015, several scientists gathered and then published this revised version of the science book, which describes in detail the science cases of the SKA-O. More than 1,300 authors contributed to about 100 papers in 2,000 pages. In its two volumes, purely because the printer couldn't buy more than 1,000 pages, have to be split into two. Together they weigh 10 kilograms. So that's your carry-on luggage, done. So I didn't bring one with me. So I don't have free copies for you either. But you can download it on the web. They're actually free if you want to just read as a bedtime story. So here, the SKA-O have, since the beginning, formed science working groups. These are all sort of the science cases that this instrument will tackle. From cosmology to cradle of life, the Dark Ages, which is the epoch of reionization, which is an area between 300 and 400,000 years after the Big Bang to about 4 million years. We don't know what happens when the gases start reionize. To all the way to the transients and pulsars, which is another very fascinating science case. But it's not just about the science. SKA wants to have a wider impact, and we have local impact. So here in Australia, for example, we had, as part of our activity before construction, we had to sign an indigenous land use agreement in order for us to be able to construct in Wajarri land, which that happens in 2022. And we, as part of the ILUA, we have partnership with the Wajarri Yamatji community in order just to involve them in the construction and of the instrument. And we got about 70% of indigenous employees in Western Australia that helping us constructing. So also we have a global impact in terms of using renewables, technologies innovation, which I'm going to talk a little bit about dealing with big data. Open science principles, we will make the data available after a proprietary period. And we are engaging actively in protecting the dark and quiet skies. We have chosen these locations because of being away from radio interference, and we need to protect that. As you have heard over the last few years, there's some companies that are sending satellites to provide some internet coverage across the world. However, those ones produces interference both from optical as well as from radio. But we are engaging and working closely with them in order for us to be able just to do our science. So how do we do this? So we've been doing this for several years. We call the precursors. So at the top there is the Meerkat, which has 64 dishes in the same location as the SKA-Mid. They've been operational since like 5 years ago, producing great science. Here in Australia, we've got the Murchison Wide Field Array, MWA, which is will be on your right-hand side, on the middle, as well as the ASCAP telescope. They are located in the where SKA-Low, and they have been producing fantastic science since almost a decade now. So, update. Yes, we are building it. In South Africa, we have, this is a photo of the container, the shipping container, which carries the antennas. The fibers start being laying out, as well as construction of the protection of the zone, the RFI zone in South Africa. They started actually building the engineering operations centers in Clairefontaine, or near Clairefontaine, where the engineering team will be located. Here's a few more pictures of the Karoo area. But the most important part of it is we already have 4 dishes installed. And just a few weeks ago, they have produced the first fringes, which is the output of 2 antennas. So that's just a significant milestone for the SKA-Mid. And here in Australia, we have to start building the antennas. So we have actually assembled and installed more than 15,000 of the antennas on the ground. That's a video of the ceremony of the first antenna that happens in 2023. So we have installed the remote processing facilities. So each of the stations, especially the outside of the clusters, they have a remote processing facilities, which is a container with all the equipment. That has been already installed. Yes, we got the system running. We actually have 4 stations already system integrated and fully operational since the early 2025. We have laid out quite a lot of fiber, antennas. We've got a construction camp, fully operational, with a capacity of about 200 beds, and most of the time is full. That's me, just part of the inspection of the cluster that we have in Perth, collecting all the data that comes out of the stations. I had more hair at the time, And then this is the other photo of the team activities happens in a meeting. We meet regularly in terms of planning as we plan our development every 3 months. I want to share with you, this is a drone footage done almost a year ago. This is not an animation, this is actual people there. This is how it looks like, the station, the 256. This is station 8. Doesn't mean anything probably to you, but it's very important for us because it is the first station we became operational. So this is how they look like. They are clipped into a mesh. And one of the significant milestone that happens for the SKA-Low in Australia happens in March last year, where after the 4 stations we did the first image. That made the public outreach in March 2025. That's the image with 4 stations, which is remarkably high quality. We're expecting that sort of a quality in about 6 months from now. And then in a year and a half, we'll be having 300 stations. When we finalize to 512, this is how it will look like in terms of quality of image. And this is give you a perspective of what this is how important this instrument will be. So, yeah, we are building it now, and this is sort of a milestone on what's coming. So we are commissioning 4, we're building 16 as we integrating 16 as we speak. We will have 68 stations by the end of the year, early next year, 307 the following year, which is, at that time, in about a year and a bit, we will begin science verification, and this is the really exciting time. We are actually hoping to get the cycle 0, which is the first call for actual real science, in 2030. So we're getting really, really close. But this is and I can see a lot of people who is in the software world. I'm a software engineer by also trade. So yeah, we've seen, and I show you a lot of the pictures of the hardware stuff, the antennas, the fibers, and roads. But a lot of this happens in software. And the journey of this happens from the photon to an exabyte starts from here, from when the radiation radio waves emitted by objects in the universe hit the antennas, gets collected by both the antenna dishes and the antennas. They get digitized and then shipped to optical fibers, transport this to the CPF. In total, we will have 100,000 kilometers of dedicated fiber. To give you a perspective, that's enough to get us a quarter of the way to the moon. That's the amount of fiber that we're putting. And then we'll hit to the central processing facility where the signals are combined together. And what they do is they get, using the first part of a Fourier transform, they channelize. and it gets converted into fine channels, so 60,000 channels. I hope this is getting out. I can see Andrew here. Just hopefully I got the 65,000 channels correct. Yep. And then, but this is not the end of the story. And then we get transporting all of that over hundreds of kilometers, and then split into different type. There is a time domain data, which is used for mainly pulsars. But the one that is a more challenging one is the imaging, what we call the visibilities. It's when we combine signals from multiple stations, we multiply them, we in phase, and then we generate each samples per baseline, per pair of antenna or station. That is the and that is the first stage, and that's what we call the raw data or visibilities, because radio telescope cannot take pictures like optical ones. We use these visibilities and we use another Fourier transform and algorithms to convert into images. And this happens in what we call the science data processing, or SDP. And this is going to be a dedicated high-performance computer. In the case of Perth, it will be located in Pawsey. It's not going to be using Pawsey resources. It's actually going to have a dedicated supercomputing. And this is where all the mathematics, the algorithms, and the complexity happens to convert these visibilities into images, which then is going to be transferred across the world into the regional centers. So the SKA Observatory, the observatory in its own, is not going to be delivering the science directly to the astronomers. They're going to be delivering to the regional centers. From then, the astronomers around the world will access the data to continue and pursue the actual science. Most of the member countries are having and developing the regional centers, including Australia. There's an existing collaboration called OSSRC, who are actually developing the regional center for Australia. So here is a summary of the data flow. And just to give you a perspective of this data size, because this is a big data challenge. We're generating 5 terabits per second of raw data, and then will be 700 petabytes per year towards the regional center. And the current requirement says that we have to keep the 700 petabytes per year. So approximately 300 petabytes per telescope. You can imagine, even with the current technology, it is a challenge to keep this. And cost, of course. So our SDP will be located in Perth in the Pawsey Center, and we'll have a dedicated supercomputer. We'll probably need about a 50 petaflop machine in order to be able to keep up with this incoming data. So we need a lot of software. And I don't expect you to understand this, and I just put it here for context, because we have split the software into multiple parts, more components, from the platform services on your left to the control system on the top, glues everything together, and then the distinct areas where the data gets transformed from voltages all the way to visibilities, all the way to images. But I put this in context to give you, because this is the point of where I guess becomes a bit more relevant to this community, because our reliance on open software is key, and it was a decision that we made from the beginning. So before construction, we developed the standards of principles, and that's a snapshot of how it even has a different logo in time. It was started in 2016 on the way to the latest version in 2021, and it set up the foundations of our way we're going to develop the software. And we say that we prefer open source software first. We establish a permissive license model. All our software is BSD3, and then and we review any piece of code or any piece of software that we going to or need to use. We decided on Python as the default programming language, but others are, when required, when Python, there's some reasons that, for example, for performance, or even the existing code that is already being well used and debugged, is in a different language, we can. And we got modules that are in C++. And we also have JavaScript for mainly the web UI. We are a Linux house since day one. All our telescope is underpinned by Linux systems. We mainly use Ubuntu, but I know that for some other areas we are using CentOS. We recently procured the supercomputer for the SKA, which is a evidence system. And to be honest, I actually don't know. I think it's CentOS or might well be Red Hat. I don't know. We also said that we're going to be doing containerized applications, but we also established a community-driven development. We are developing we have about 250 software developers scattered across the world, about 40 teams developing the software. So in the area of platforms, I have this picture which represents all the layers of the platform. Nowadays, well, back in the 90s, we used to deploy software. We used to compile software. All right, I don't know if you still do that. But nowadays, we just deploy Docker containers. So, but then from the software development, it became a little bit easier. But it means that you need a big infrastructure to be able to run it. So we actually have a private cloud infrastructure. We have a lot of open source, and we rely on them, like Kubernetes, OpenStack, and Ceph. That does require a lot of skill set. Even though you don't pay a license fee, this is free, but it does require a lot of effort. It still costs some effort in terms of a skill set. In the data processing, we have a lot of domain-specific rate interferometer algorithms, and we spend a lot of our R&D. We have a very niche community in there. Most of the software is still open source and have an open source license, but it's very small community in terms of development. However, this is scientific computing, and that broadens the community a little bit more. And we're using tools in there for, like, for example, SPAC, which is a package management for this type of software. But we also rely on another type of open source like Slurm, and if you're familiar with it. In the observation operations, which is more of the front-end side of it, most of it is web UI, and that symbol, who recognizes that symbol? The one in the middle, next to Python. Yeah, it's React, yes. That's one of the main choices for framework. But one of the key decisions, and I think a truly commitment in terms of the open source, has been the story of Tango. Not Tango the dance, this is the Tango controls framework. Back in the 2015, during pre-construction, the project is still deciding how we're going to build the control system. And when you build a large-scale control system, distributed control system, you get a lot of choices. You go commercial systems like Siemens and what we call traditional SCADA systems, or you can go open source. So we went out there and looked into experimental physics facilities that uses, and this is one of them. There's another one. There's a couple more. So we took 2 years plus to evaluate, and through prototyping. But one of the things that was interesting was the actual decision, because you got to a point where, have you heard analysis paralysis? How much effort and time you're going to spend with deciding into which way you're going to go, because none of these are perfect. They're always trade-off. And also, not only the trade-off, but there's also people who are advocate for one or the other because they're more used to it. This is, I mean, we've seen it in the software development for years. So you could get to a point where, well, not making a decision is actually costing you more than actual, even if your decision is not 100% right. So that happens about 2017. We couldn't wait any longer. And it was a meeting gathered by the SKAO, hosted by the SKAO, and gathered all of the key individual players. And at that meeting, the decision was made. And it was made by Tango, using Tango. And I think even though the competing technology was not happy, however, I think in the overall thing, it is actually was useful because the cost of not making the decision will be much huge than using, even though Tango is not perfect. That means we do need to require active contribution to the community. And we are quite of an active contribution to the code base code of the Tango community. Tango is a control framework that used in a lot of synchrotrons, in the Europe in particular, and we are really key contributors to the code base. So it helps not just us, but it helps the community. And we also use some of the tools that they have developed, like, for example, a visualization tool they have. Other things that we use in the terms of open source is, you are familiar with this, the Grafana. That has been a very important tool for us. A lot of the existing monitoring system are built on using Grafana daily, as well as using Jupyter notebooks in terms of sometimes running some ad hoc experiments. So I'm going to leave you with a, this video was made by the comms team as what happened in 2025. I hope you enjoy it. The base of the station for the SKA-Low. That's a massive building. Having a supercomputer facility in the outdoor. 21 modules were actually welded, one by one. Welding. I have all of the refractory camp. The actual antennas are assembled by people, manually assembled, push through it, clip into the mesh, stuff there. You can imagine. Right now, for example, it's 45, 50 degrees. It's quite challenging. Before I wrap up, I just want to share something with, because do I have a bit of like a couple minutes? I know Kylie just in the morning just started with about her experience, and I wasn't sure I'm going to be having time to, but I do want to share with you something about my story. So I've been in astronomy or involved in astronomy for close to 30 years. My background is in electronics engineering, computing engineering. I did my degree in Chile. And at the time, Unix was main thing, but even Unix wasn't open source. When I started at the observatory, the European Observatory in Chile, the system there was Unix-based HP Unix systems, closed source, nothing really open at the time. And I think through my experience back in the late 90s, early 2000s, as I started as a software engineer, I was hired as a software engineer, and I had the privilege to develop a lot of the instrument software, and we start getting more exposed to open source, like open languages like Python, we moved to Linux. We started transitioning from Unix-based to Linux. We started actually developing our own. They used to have a SCADA application for the control system, moving away from it, because the advantage of not only not paying a license fee, but also the being able to be part of our community, it was just super beneficial. And then I moved to Australia in 2007, and I had the opportunity to join the ASKA telescope. And during that time, I also had one of my job was to choose the control framework to build the ASKA telescope. And I went out of there to the community and search for what is there, because I didn't want to build it myself, neither I wanted to pay, or we didn't want to pay something unless it's really necessary. So I went out there, and it opens up, and I had the opportunity to meet a lot of great people and join this community of the synchrotrons on the high energy physics, where I got in touch with the Tango, with others, with EPIX, which is the other one, which was ASCAP. Was built. And it took me a year to evaluate and go through the process to evaluate these frameworks. And because when you do things like evaluation frameworks larger like this, it gets rooted in the architecture, almost like a marriage, all right? So, so you need to be assured you're at least good enough to make the decision. But and after completing the ASCAP, I moved to the Square Kilometre Array. So I've seen the journey from closed source all the way to open source, and I think, and I have to say that I am so grateful to have a community, to have the ability now that not only choose great software and use software, but also to contribute to that community, and it's very important. So if you do end up having and relying on open source community, it's just putting back as well is important, and that's the approach at least we as the SKAO have put into the Tango community. And on that note, I finish, and thank you very much. I hope you enjoyed it.